Okay, geometry students, we are back. Alright, so this is a challenge problem. Not really though, but it'll help us understand a couple of things. Okay. So, 1, 2, 3 parts of an equation here. Okay. So, important part here I think we're learning in this one is lateral area. It says, what is the lateral area of the prism at right? Now, lateral area, that's different than surface area or area, okay? Surface area means you would be wrapping the whole thing in wrapping paper. You got a prism that came in a hexagonal prism box, and you'd wrap the whole thing. You didn't want any sides exposed, so you need the wrapping paper to cover both ends and all around. Now, lateral area means I just go around the outside where the rectangles are, okay? In the case of a cylinder, it's different. So here's a cylinder. If you guys ever seen one of these before, this is a, what you would call it? A paper towel cylinder, right? It's on here. So tomorrow we will be talking about cylinders. That's a great way to end a week. Surface areas of cylinders. Maybe my favorite way to end a week. But the surface area of this cylinder, well, there is no surface up here. I can stick my finger through. So if I'm looking at a paper towel roll or a toilet paper roll, there is no surface here. Because look, I can go right through. In there. See? So there's no surface here. I'm just concerned about this surface on the area, on the outside. The area of this. Now, we'll figure this out tomorrow, how to do it this. But the only type of one that I could explain is what I had there. So imagine that this is some sort of like hexagonal shaped, you know, paper towel roll. Okay. So they just want to know the area of all these rectangles. That's not so bad. That's actually pretty easy. Okay. So each rectangle here, if you look at this carefully, if we took it apart, you would see that each rectangle had one side was 6 and the other side was 12. And the area of a rectangle is just base times height. 6 times 12, we did that before. 6 times 12 is 72. So each of those little rectangles, this is in meters, is 72 meters. But there's 1, 2, 3, 4, 5, 6 of them. So what I have to do is say, well, each one of those rectangles is 72, so I have to go 6 times 72. Or you can add it up, 72 plus 72 plus 72 6 times, but that's, to me, too much work. So I'm just going to do 6 times 72. 6 times 72. Oh, wrong button. Oh, that's a big number, but that's okay. We like big numbers, especially if you have a calculator. So the area, the lateral area, or LA, of this particular object is 432 meters squared. That doesn't include the endpoints. That would be like if it was a paper towel roll. Now, the next thing is, they ask, what is the area of a base in simplest radical form? So they wanted these bases. How much is one of these bases? Okay, this is the one that's tricky. Okay, this is where the challenge comes about. This is how we're going to solve this one. Okay, so first thing I'm going to do is I'm going to look at, it's a regular hexagon, right? If we remember the formula for the area of a regular hexagon, or any regular polygon, if you remember, is A equals 1/2 A times P. Okay, so I need to know two things. I need to know A. Well, A is the apothem. And an apothem I have highlighted here in red. It goes from the center to one of the sides. Now, an important thing to note here is it makes a right angle. which is, of course, as we know, 90 degrees. We'll come back to that in a second. The other thing we have to know is perimeter. Well, a perimeter is just the number of sides, if you remember this, number of sides times side length. Now, if we look back in here, we saw each side is the same, right? So they're all 6. So going around here, I have 6, 6, 6, 6, 6, 6. All of a sudden, the devil has appeared in my kitchen. No, that's not true. Hold on. All right. All right, next. So there's no devil here, so I'm okay. So, now, number of sides is 6. Oh, my God, and another 6. The side lengths are 6. So, P equals 6 times 6, which equals 36. So, the perimeter is 36. So, I got half this problem done. And I still haven't seen the devil yet. I'm a little worried, but okay. It was 1/2 A times 36. Okay. Okay, so we just got to figure out the apophyte. Well, here's the problem. They made this problem extremely, extremely, extremely tricky. Okay? It's a dirty problem, I think especially for a geometry class. But, okay. We'll deal with them. We're not going to let them intimidate us, guys. I'm going to do this. Well, I'm going to say I want to find this apophyte. How do I find it? Normally, they should give it to you. I think they should give it to you. I honestly don't know what it is, though. But I do notice something. I have a right angle here. Okay? Now, if I have a right angle, and I do this, I suddenly have a right triangle. Okay? Now, what happens is I realize, well, if I notice this is 90, I wish I knew what this was and that was. Okay? Maybe I can use some form of trig on this. Possible, right? So I'm going to do this. I'm going to think about it this way. I'm going to draw all these blues in. Now watch what we do here. We're going to draw. These are what we call, of course, the radius of this hexagon. The blue lines. I don't know their value, but I'm drawing them for an example. And we don't really need to know their value. We could figure it out. I'll show you in a second how we're going to figure it out. But, to me, a very tricky problem. Okay, so 30, 60, 90. Look at this. So, what is this angle? Well, this angle here is one of these, right? So, if I'm looking about this angle, let's say, or this angle, I have 6 of them here. 1, 2, 3, 4, 5, 6. But I know they make a circle, and they add up to 360. More 6s. There's so many 6s in this problem. It's weird. 60. So this angle is 60. This angle is 60. This angle here is also 60. But it's being cut in half by the red thing, so it's actually 30. So, knowing that all triangles, this is so complicated. Knowing that all triangles add up to 180 degrees, 90 plus 30 is 120. 180 minus 120 is 60. So it's one of our special triangles. There is no other way to do this unless you use SOHCAHTOA. Can I use SOHCAHTOA here? Yeah, I guess so. Okay. Another thing I know. When I look at this sucker here, this whole thing was 6, but this cuts it in half. So this side of this triangle here, the one we're looking at, I'm going to maybe highlight in green, the one we're looking at as 3 over here. 2 ways I can go about this. What I can do is I can realize there's a whole bunch of triangles here. I could keep doing this to every side. Okay? And I will get a number eventually. because I can take the area of this triangle. Oh, I still don't know the height. I still have to find the height. Can't do that. What I can do is use our rule. Okay, so if you remember a 30, 60, 90 triangle, let me put this the right way so it doesn't, oh, I did it right. Looks like this. Okay, if this is x times the square root of 3. And look at that. As I pull us away, our x is 3. So this one here has to be 3 square root of 3. All of that. They expected you to know all of that. So my apothem is just 3 square root of 3. Otherwise, this is a terrible, terrible problem, and we're not getting there yet. We're not done. And what they say in the question originally is in simplest radical form, which also means that I can't really do trig here. That was my whole problem with doing trig, is that if I tried to do trig, I would have got this in a decimal form, because that's the way the trig functions work. So, all right. Now, as we're moving on here. So I'm just going to put this in here. A equals 1/2 3 square root of 3 times 36. Okay, so what I'm going to do is I'm going to multiply this, by this, by this, and leave the square root of 3 out. Because this is really 3 times the square root of 3. So I'm going to multiply all these together and leave this in. So what I'm going to do is say 1/2. Remember, some of you like decimals, you can put 0.5 there, times 3, times 60. I messed that up. 1/2 times 3, I said 60, times 3, times 36. And I get this number. 54. So the area is 54 square root of 3. 3 square root of 3 cannot be simplified, so I leave this. 54 square root of 3, what is this even in? Meters squared. Now, next part. We're not done yet. This is why this is such a terrible problem. So, the area of the base, of one of the bases, in simplest radical form, we did on the other page, equals 54 square root of 3 in simplest radical form. What is the surface area of the prism rounded to a whole number? Okay. Basically, you add the surface times the base, plus the base to the back. So it's all these parts combined like we did before. So the lateral area covers all these rectangles. So I didn't have to do all that over again. So lateral area equals 432. Now the area equals 54 square root of 3 of the base of this. All that mess that we had to go through. Plus, there's another one on the other end. If you wanted to, you could multiply these two 54s together, and you would get, I don't know, 54 times 54, and I'm not going there. Let's not make this too complicated yet. Okay. So 432 plus 54 plus 54, I can't really add these two together, these three together. I can add these two together. So I got 432 plus 108 square root of 3. Now they want it rounded to the nearest whole number. So now I multiply this in the computer. So I'm going to, calculator. 108 square root, clear, second quick. 108 second square root of 3 is 187.061. 432 My head hurts. I don't know about you guys. But at this point, I just want this answer because I've been working on this for so darn long. So I'm going to add that to 432. 619.06. They say round to the nearest whole number. That means 0.06 is not, this is a 0. I need to be a 5 to make it a 620. So I am just going to say the final surface area of this shape. After what? Is this like, have we been on the air for like 2 hours now? 619 meters squared. Wow. But it was a good challenge. I liked it. I had fun doing that. I know you guys are probably like, playing just crazy. But I am. Okay. Guys, have a great day. I'll talk to you later. Bye.